Yeah, okay. So uh, we were talking about how free energy is affecting uh, equilibrium and how parameters such as temperature or pressure would have influence on that. So we spoke about temperature perhaps, then we can go to the, so we talked about some of the aspects here, where how the molar free energy changes with temperature for different systems and what the slope of the curve means and what the curvature means. And then we figured out what the changes of free energy happens during some sort of process, be it solid to liquid or liquid to vapor, or any process as such. Then how the free energy is dependent on temperature, and we try to break it down as to how the free energy change with temperature is computed from uh, the various parts of it. And you go back to the basic equations such as delta H minus T delta S, and that gives you the total energy calculation, which is the Gibbs free energy. And delta H has got dependence onto temperature with through specific heat, as well as delta S also has dependence with specific heat, and that's how it changes with temperature. And then you figure out the energy contribution from the entropy part and then sum it up. Uh, um, that's what is given here in this slide, which eventually computes the free energy. Excuse me. And depending on the sign of the free energy, you'll be able to find out whether the process that you've been talking about is going to be feasible in the given conditions, or is it not. Okay, and how delta G is connected here. So we talked about a very common example, which is water, and then its solid to liquid state, and how it changes. Okay. um, and then we can perhaps talk about another aspect, which is, uh, can we make it full screen? Control L. Okay. Now we can talk about another aspect of the free energy and how it depends with pressure. All right, we talked about temperature, we talked about, now we can talk about pressure. So if you go to the basic equations of dg again, like we talked about the variation of free energy with temperature, from the expression dg is vdp minus sdt, and that's how with a constant pressure you could find out that the partial of g versus g over t is related to entropy and negative of entropy. And likewise, you could see that if you fix the temperature per se, then the dg is vdp minus s dt. Equation becomes dg at constant temperature is nothing but vdp. All right, and when you take a partial of free energy with pressure at constant temperature, it is nothing but volume, right? And this is a generic form, and that you can find out for a solid system. Okay, and the same thing for this liquid system you can find out. So if we talk about water, then we'll see that the partial G by P of solid water is the molar volume of solid water. Likewise, partial G by P of liquid water at constant temperature is the molar volume of water itself, liquid water. Right? So now, like you talk about a phase transition from solid to liquid, for example, like ice converts to normal water, then the change in free energy can also be related to the partial of del G over P at constant temperature here is a mistake. It has to be del V. And what is del V? Del V is the change in the molar volume of liquid substance minus that of the solid substance. What is the incremental change in volume? Right? So that is so in a way you could see that no matter what the material you have, the del G over del P, or the partial of G by P at constant temperature is volume itself. All right, and what does it tell? Volume, it's a positive quantity. It's a, it's always a finite quantity. It cannot be a negative quantity. So if this ratio or this partial ratio is a positive quantity, and this means if you plot Gibbs free energy here, and then you plot pressure here with delta T being 0, then you got to get something with a slope which is a positive slope. Okay, which is what is given here. Okay, now you come to the exact phases, then you come to the solid phase or the liquid phase. For the solid phase, you'll have a graph which will represent the solid slope, which is the volume of the solid of the substance, the molar volume of the solid substance, and this slope is indicative of the number, that quantity, that's a physical quantity. And likewise, you can have del G over P of the liquid phase, and this curve, this slope is going to give you the molar volume of that. Okay. Now, if this is the graph, then can you figure out what is wrong with the graph? Any guesses as to what is special about this graph, or what is wrong in this graph? No, nobody sees anything. So let's say I'll give you the clue. So this is if we look at the graphs of the solid phase and liquid phase, the same substance. We're not talking about a solid of some X material and liquid of some Y material. No, we're talking about X solid and X liquid. Okay. Now, ordinarily, you'd see that if you increase the pressure, what happens? Which phase is more stable? That's why it's written the Le-Chatelier principle, which is typically applied to gases, but then of course you can make this is natural principles. You can perhaps make use of that. So normally what happens when you apply pressure to a material, okay, which phase do you think is going to be more stable? If you apply pressure on material. Any answers?
Liquid phase.
Liquid phase is going to be more stable when you apply pressure on a material? Or this is something that you're telling from this graph?
Sir, in general, liquid phase is more stable to applying pressure.
I mean, why do you say so? I mean, do you say that solids are not stable when they are loaded with pressure?
No, sir, in comparison to
yeah, in comparison. We are talking about in comparison to solid and liquid. We are not talking about vapor phase here.
Because when we pressurize gas also, it tends to convert into liquid phase, and same goes with solid also. When we apply pressure, it tends to change state to liquid.
Oh, solid को apply pressure apply करो तो liquid बन जाता है?
No, not exactly like applying pressure makes it liquid, but when it is subjected to increased pressure, the phase transition is more quick.
Okay, you have a point. We'll discuss that point, going forward, preferably in this class itself. But then a general thing, one thing you made very clear is that when we apply pressure to a gas, it becomes a liquid phase. All right. Class, is everyone attentive? Yeah. When we apply pressure to a gas, it generally converts to something which has a lower volume.
Sir?
Yeah.
So if the pressure is increased, then I think the liquid phase becomes unstable. Means with respect to the formation of that solid phase. That there comes a role of pressure, which you say
Yeah, so what you're
the
saying that
least
if you increase
attached
the
principle.
pressure,
Then
solid will
the
become more stable.
yeah.
Okay,
Liquid phase will be becoming the means it will become unstable.
unstable one. Okay, yeah. So okay, so the thing is, if we apply pressure to uh, a gaseous state, okay, it gradually converts to a liquid state, isn't it? That's what you use in what the fuel gases, that we use for cooking gases. What is it? It's LPG, no, liquefied petroleum gas. Now, like, so why does it happen? If you look at apply Le Chatelier principle, PV is constant, isn't it? It's as simple as that. PV is constant. Multiplication of P and V is constant. So increase pressure, volume has got to decrease. All right, and that we sort of apply that principle in the gaseous state itself. But then you cross boundaries, when you load more and more, then eventually the material is going to take up a form which has a low molar volume, isn't it? Let's talk about the molar volume of gas. It's about what, 22 odd liters. But talk about molar volume of the same gas liquid, it's going to be much lower. So it takes up a form which has a low molar volume. Of course, proportionally the pressure is to be really high to be able to do that. The fact is that applying pressure actually makes or transforms the gaseous state to a condensed state, okay, which is the liquid state. Okay. But again, if you go forward, then if you compare the molar volume of liquid and solids, all right, which one has a lower molar volume?
Sir,
When we
in
are
ice or water, it shows anomalous expansion thing also. So we
okay,
have to
that we are that is what I was trying to come to. Okay. So yeah, very correctly pointed out. But ordinarily, when we talk about lower molar volume, whether it's a liquid state which has a lower molar volume, or the solid state which has a lower molar volume. Any ideas? Any participation? Okay, if you let's make it rather simple. Which one has a higher density, grams per cc? The solid or the liquid? Typically, it doesn't have to be very specific answer. Ordinarily, you know that solids are substances where the atoms and molecules are, typically are in a more organized, more ordered manner, and the packing density is much more efficient, much more stronger. All right. So in a confined space, you're able to put more and more atoms and molecules into that space. So eventually, the density of the material becomes high. That means the typical molar volume of that material is going to be lower. So, not talking about exceptions, when you talk about molar volume, gaseous molar volume is the biggest, then the molar volume of liquids, then the molar volume of solids. All right. If that is the situation, then what's going to happen is that here uh, in a high pressure domain, okay, something which is favorable to occupy would be someone which has a lower Gibbs free energy. All right. In that sense, the way we discussed that, it comes out that if you increase the pressure, solid is going to be something which is going to be stable. Okay. If solid is stable, or something which some phase is stable, then that phase must have lower free energy. Whether here it is slightly different. Okay. And there is a reason for that. Right? Let's talk about it. What's the reason? I think this one will give you all the people a clue as to what is so special about this water system. All right. What do I mean with this is National Geographic photograph. Deep inside some lake where the temperature is sub-zero. Well, it's a negative temperature out here. Okay, but then the fish or the aquatic life is able to survive here, and this is beneath the water surface, right? And the lake is completely frozen. So how is it possible? I think some of you know the answer. I'm asking someone who doesn't know the answer. If one doesn't know the answer, you would like to make an attempt to sort of, see what the answer could be. Anyone? Okay, let's cut. As someone was saying, what Divyanshu or Divyajuti was saying, that if you have there's an anomaly with the solid to liquid transition in water. All right, it's around that transition point. Okay. Okay, let me ask you another example, another question or observation, if you will. If you have ever used a refrigerator, and that we use in our daily practices in home. Now, if you fill the water, completely fill the water bottle, and then put it in a freezer, all right. Uh, any idea what could happen? Let's say I open up a bottle, a plastic bottle, sort of the kind of water bottles that we use, and I fill it to the neck, all right, and then I cap it off, and I put the filled bottle into the freezer part in the refrigerator, all right, and I let it freeze. What happens?
The ice will expand, so the bottle cap will try to open it. It's the
All right. Okay. So someone perhaps has used only the refrigerator. The rest of the people, they've never used it, or they've never fiddled with odd things in the refrigerator. Exactly. That's what's going to happen. If you fill the ice, fill the water, and then put it in a freezer and let it freeze, what's going to happen is that at some point it will probably crack your bottle, or at least what it will try to do is, get the cap off. All right, it'll be in a bad shape. The bottle would be in a bad shape. Why is that? Because the 1 liter of water that you filled up, when it converts to ice, that doesn't remain 1 liter anymore. It requires much higher space, much higher volume, at least a little higher volume than 1 liter. And then when you capped it off, you're confining the volume to 1 liter only. That means the water, the ice that is there inside the bottle, 1 liter space is not enough. It's trying to expand it. So the fact is that ice or the water system upon freezing becomes a lighter substance. All right, that means it's the crystallographic arrangements in ice is in such a way that the water molecules stay slightly apart from each other than they would ordinarily remain in the water system, in the liquid system itself. As a result of which, the same 1 mole of water molecules to be kept in a solid space, a solid phase, they require more volume. All right, which is the anomaly, which is anomaly because it ordinarily doesn't happen in other substances. All right, when you take a mole of iron or steel and then you melt it, you'd see that the volume would expand. But when you take a mole of ice and then convert that thing to water, you'll see that the corresponding volume would decrease. So as a result of which, in the water system, ice is lighter than water. Lighter meaning it has got less density than water. And that's the reason if it happens in a water body, the ice or the crust floats on the water body. It can be a small body or a big body, it doesn't matter. So aquatic life can actually be fairly, alive and kicking inside the crust where the top surface is ice, and then the bottom surface becomes heavier, and then the water actually comes down, and then it can the aquatic life can actually exist. And to also, you might know that there is a subtle temperature of 4 degrees where water is the heaviest. So if you go well beneath the surface, there's good possibility that the life is, and the water is not even 0 degrees Celsius. It will be slightly different, and that's the heavier part, and then that goes to the bottom. That's where aquatic life survives, thrives. So that's it's a natural process, and then it's important that we need to understand how that is represented in basic thermodynamics. All right. So that is something we can get from some of the relationships, which is one of the relationship is the Clapeyron equation. Now we have talked about how the free energy and its change, or how equilibrium changes with the change in pressure, how equilibrium changes with change in temperature. Okay. Now, what could happen if there is a variation of both pressure and temperature? Okay, what could happen? Okay, so that gives you some idea, and this Clapeyron equation gives you some ideas where if there is a change in pressure as well as temperature, then what could happen? So if you go over this, it's a kind of a fairly simple derivation, which talks about equilibrium in a situation where both pressure and temperature could change. All right. So let's talk about two phases, the same discussions of ours, solid and liquid. And when you say that they are in equilibrium, then you would say that the molar free energy of the solid system is equal to the molar free energy of the liquid system, and that's why these two phases are in equilibrium. Okay. Now, when there are small changes in those two phases, you can write that dG, the small change in the free energy, molar free energy of the solid state, is equivalent to the same in the liquid state itself. Now, if you expand that, the dG is VdP minus SdT. This is the most important relationship that we have been working all along. And for this generic formula, you can apply this formula for dG in the solid state or solid phase, as well as dG in the liquid phase. Okay, and that would correspond to the V of solid dP minus the entropy of solid dt. Likewise, for the dG for liquid is V of liquid dP minus S of liquid dt. Okay. Now, when we say that the equilibrium still is maintained, that we are both the solid and liquid phase are in equilibrium, then you can equate these two. Okay. Now, when we equate these two, you can actually come with a simplification of this, which comes out as del P del T, the partial of P by T in the equilibrium state is actually the del S by del V. This S solid, S liquid, and S solid, S liquid, V solid, V liquid. So depending on, you call to solid to liquid transition. I mean, this is liquid to solid transition. That's why it is S to L. Likewise here also, products minus reactants, or the final phase minus the initial phase. So that is del S L to S transition. You can eventually write it for S to L or L to S transition, doesn't matter, as long as both of these two are same. So now we are coming to an equation where del P by del T is del S by del V, and since del H is T del S, because del G is del H minus T del S, and when we talk about equilibrium, del G is 0. If del G is 0, del H is equal to T del S. So what we do is, instead of del S, we write the term del H by T. So that gives me an equation where del P by del T is equal to del H by T del V. Okay, this is the Clapeyron equation, and this can actually give you a lot of clues about what happens in solid liquid phase transition in any system for that matter, and how that can be represented in phase diagrams. We'll talk about some of these things. Now, okay, now are you familiar with something like this? The picture here? This is called ice skating.
Yeah.
Yeah, you might have seen in, people do figure skating, and people, otherwise also they move on a skate. And this is, they're moving on the surface of thick ices, and then what you need is a kind of a blade, okay, that is beneath your shoes, and it sort of rests on a very small cross-section line, which is this, okay. And how does it work? How is one able to slide through so swiftly that nothing really happens? They don't fall off, and they're easily they're able to glide through. So what's the and how does it work? Okay.
The pressure,
Yeah.
sir, the pressure from the skates reduces the melting point of the ice. And when the skater slides from the ice, um, it it then refreezes. So this lets the
Absolutely,
skate.
absolutely, wonderful, great. So that's what happens. So let's go to that and then see what's happening here. Okay, if we look at the Clapeyron equation, then we're talking about solid to liquid transition, and then you know that when you talk about these skates, we are talking about something related to ice. Okay, and what is happening here is that for the solid to liquid transition, from ice to water transition, what is happening is, what about the del H there? For the solid to liquid transition, for ice to water transition, what is del H? Del H is a positive quantity or a negative quantity?
Positive quantity, sir.
That's a positive quantity. That means it's an endothermic reaction, isn't it? You got to put energy into the system to be able to make water from ice, right? You have to supply energy. Okay. If that is true, then del H is going to be a positive quantity. Now, for the same system, that means solid to liquid transition, what is del V? And del V is what? Del V the change in molar volume. All right, change in molar volume. So for the solid to liquid, that means the ice to water transition, what is the change in molar volume? Is it a positive quantity or a negative quantity? That means volume is lost or more volume is obtained when ice changes to water. We all this while we talked about it, right?
Contracts.
Contracts.
Yes.
Contracts.
Yes,
what contracts? Ice contracts or water contracts?
when ice is formed to water, the volume gets reduced.
Okay, so the ice becomes water, so this much of ice becomes this much of water. All right. Now that is, so what is del V? Del V is a positive quantity or a negative quantity then? For this
Negative.
reaction, solid to liquid, del V is what? Positive or negative?
In case of ice, it's negative.
In case of why? No, we are not talking about in
Ice.
case of ice or water. We are
Oh,
talking
in
about
general.
a process.
Oh.
When we're talking about del V or del H is not about water or ice. We are talking about ice to water transition. For the phase transition of ice to water, what is del H? You said positive. I said yes, I can accept that. All right. Now, what about del V from ice to water transition? The same ice to water transition.
Negative.
That's going to be negative because you had this much of volume with ice. Now, when it converts to water, it's got this much volume, smaller volume. Okay, so del V is yeah, the smaller volume minus the bigger volume. That's going to be a negative quantity. All right. Now, if you look at the right side, That's a positive quantity on the top and the negative quantity at the bottom. What happens to the total quantity? That's a negative quantity.
Negative quantity.
All right, so this one is negative quantity, and we are talking about equilibrium here. We are talking about equilibrium between ice and water, and typically that will be, happening at 0 degrees Celsius or 273 Kelvin. Now this is a negative quantity. When I increase the pressure here, all right, if this quantity is negative, when I increase the pressure here, what is going to happen to del T here?
It needs to decrease.
That should decrease.
It will decrease.
Absolutely, because when I'm increasing the pressure, I'm putting a positive number here. All right, and this being a negative number, this del T has got to be negative because otherwise this equation would not satisfy. All right, so the Clapeyron equation says that for the solid to liquid transition in the water system, all right, if we increase the pressure, del T is going to decrease. And what does it mean del T decreases? Del T is what? Because this process is happening, this is the freezing or melting process. Now if del T is something, this del T is the departure of the equilibrium from the ordinary equilibrium process, right? And that's going to be how positive it is from 0 degrees Celsius or how negative it is from 0 degrees Celsius. So depending on the pressure, if you're applying more and more pressure, because of this del T, this quantity would influence this quantity, and if you apply more and more pressure here, the melting point of ice is going to go below 0 degrees Celsius. All right, that means you can still have -1 degree Celsius and still have water as liquid water. All right, so that is exactly what happens. If you put a lot of pressure on this, the thin line of ice actually here they can remain in water because under the pressure the melting point of ice actually goes down. Okay, so because of that the thin layer of water can form here under the blades, under the skate, and that actually works as a lubricant. Okay, sort of helps the skater slide through fairly easily. That's one of the reasons this happens, and to an extent that's possible for skiing also, but then you're not able to apply so much of pressure in skiing as you do it in skating. All right, so more appropriate here is this one. Skatings are really important. So you can test for yourself as to what is the cross section that comes in contact with the ice crust, and then how much of pressure are you going to be able to apply. A person having that skate on, how much of pressure can you apply, and that would depend on the weight normalized by the contact area with the skate, and then you can put those numbers in this equation. This value, this value, also this value. You can put this pressure and you can find out what is the temperature change that can happen from 0 degrees Celsius, so that it will help you slide through easily. All right. So like this here we talked about two phases where solid to liquid transition we talked about, but then this also might happen that you can see some changes when you convert liquid to vapor or solid to vapor even. Okay, how does that change? That is given in something called a Clausius-Clapeyron equation. Instead of the Clapeyron equation, you have now the Clausius-Clapeyron equation, which is only the subtle change in the process from here. Okay, from here we can take it that when we talk about the del V part, okay, when we talk about del V part here, then we're talking about a very small number, in the sense that for the 1 liter of water would become perhaps 1.05 or some liter of ice. You're talking about 0.05 kind of liters for for a 1 liter system. That of course corresponding you can change. What will be the change for a mole of water? But then when we talk about the equilibrium between the condensed phase and a vapor phase, okay, that difference is going to be much bigger, because this del V then becomes the V of the vapor phase minus V of a condensed phase. A condensed phase meaning it can be either a solid phase or a liquid phase, and since there is not major difference between this molar volumes of solid and liquid in comparison to the volume of the vapor phase, you can actually write del V is the volume of the vapor phase itself. I mean, you can think for yourself, the 18 grams of water is, what's the volume of 18 grams of water? Any ideas? What's the volume of 18 grams of water? Gautam Chandra, batao.
22.4.
22 point?
22.4. So 18 grams, 22.4 milliliter.
22.4 milliliter.
18 grams. Yes.
कौन बोला? दिव्यांशु.
Yes, sir.
हाँ, और अमर तुम बताओ.
Sir, 22.4 liters.
18 grams of water would be 22.4 liter. तो 18 ग्राम तो उठा ही सकते हो. 18 ग्राम्स वाटर तो उठा सकते हो, है ना? मतलब वो जो क्या बाहुबली जैसा. अरे सारे बुड़बक बैठे हैं. मायंक कुमार हो इधर? मायंक कुमार.
यस सर.
हाँ,
यस सर.
18 ग्राम्स वाटर मतलब कितना ज्यादा वाटर होगा?
लीटर में देखें तो सर 22.4 लीटर होगा सर.
22.4 लीटर होगा. तो मतलब
Yes.
22.4 लीटर होगा तो कितना बिस्लरी बोतल होगा?
सर 22.4 लीटर का मतलब एक बिस्लरी बोतल में तो सर 1 लीटर या 2 लीटर के करीब रहता है.
हाँ, बड़ा जो नॉर्मल वाला 1 लीटर बोलो.
हाँ तो सर वो तो फिर
22 बिस्लरी बोतल आएगा.
यस सर.
ओके, तो 22 बिस्लरी बोतल जो है वो उसको तुम मतलब ऐसे ही उंगली में उठा सकते हो, है कि नहीं?
नहीं
18
सर.
ग्राम है. तुम्हारा पेन का वजन कितना है?
पेन का
पेन का
वजन
वजन
सर 10 ग्राम से भाई
10 ग्राम. यू माइट
Yes,
बी
sir.
अबाउट क्या 200-400% तुम गलत हो गए. बट एनीवे some sub 100 grams, isn't it?
यस सर.
ओके, तो 18 ग्राम्स जो मैं बोला तो
Yes,
उसको
sir.
तुम बताए 22 लीटर वाला कैन चाहिए पानी का.
यस सर.
ओके, तो 22 लीटर पानी जो है उसको तुम एक हाथ से उठा तो सकते ही हो.
नहीं सर. यस सर.
नहीं,
एक हाथ
नहीं
से
सर.
उठा सकते.
ना, तो 2 हाथ से उठा लोगे.
यस.
ओके, तो मतलब तुम इतना पिद्दू टाइप के आदमी हो जो 2 हाथ में तुमको लगेगा 18 ग्राम उठाने के लिए.
सर वो लिक्विड में सर वॉल्यूम
क्या?
लिक्विड में सर 18 ग्राम का वॉल्यूम ज्यादा होगा, इसी का आंसर लगेगा.
वही तो मैं पानी का पूछ रहा हूँ, तब से वो पूछ रहा हूँ पानी का 18 ग्राम पानी का वॉल्यूम कितना होगा? तुम बोल रहे हो 22 लीटर.
सर मोलर वॉल्यूम पूछ रहे हैं क्या?
हाँ,
सर मोलर वॉल्यूम पूछ रहे हैं क्या?
मोलर वॉल्यूम 18 ग्राम तो मोलर वॉल्यूम अगर तुम उस समझ में आया तो ठीक है. मैं तो मोलर वॉल्यूम नहीं पूछा था, मैं बोला 18 ग्राम वाटर. 18 ग्राम वाटर पानी, उसका वॉल्यूम कितना होगा?
सर 18 ml ही होगा.
सर डेंसिटी यूज करके करना था शायद इसे.
क्या 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 यूज करके करना चाहिए?
डेंसिटी.
हाँ, डेंसिटी क्या है?
डेंसिटी इक्वल्स टू मास बाय वॉल्यूम. डेंसिटी इक्वल्स टू 1000 kg per meter cube.
तुम इतना बुड़बक हो, हमको पता नहीं था अभी। तुमको 10 मिनट लग गया। कोई एक बताए 18 ml मतलब 18 ग्राम मतलब 18 ml। कोई कोई बताए, कोई एक बंदा कोई बताए।
हाँ सर।
शक्ति स्वरूप, हाँ। 18 grams of liquid water would be 18 ml। और तुम लोग तभी से
थोड़ा सा
कैलकुलेट कर
ज्यादा
रहे हो।
सोच लिए सर।
22 लीटर मुझे बता रहे हो बुड़बक। तो मतलब अब मेरा पूरा अब दिमाग खराब हो गया है मेरा।
थोड़ा सा ज्यादा सोच लिए सर।
हाँ,
थोड़ा सा ज्यादा सोच लिए, वो
तो थोड़ा
डायरेक्टली ऐसा
ज्यादा
लगा।
सोच रहे तुम लोग। या यू आर नॉट फिट टू बी इंजीनियर्स। ओके, इंजीनियर बहुत कम सोचता है, इतना सोचता है, पटाख से सोचता है और सॉल्यूशन निकालता है। ओके, 18 ग्राम वाटर मतलब 18 ml। 18 ग्राम वेपर, वाटर वेपर, उसका वॉल्यूम क्या है? अब बताओ। 18 ग्राम
सर
वाटर
रिपीट द
वेपर।
क्वेश्चन।
हाँ
22.4 लीटर।
या अभी इसका आंसर है 22.4 लीटर।
हाँ
ओके,
सर।
अच्छा 18 ग्राम वाटर वेपर को अगर 22 बॉटल में भर्ती करोगे, वो बॉटल को उठा सकते हो कि नहीं? उतना 22 बॉटल एक हाथ से उठा सकते हो कि नहीं? पता नहीं उठा सकते हो कि नहीं, लेकिन उसका वजन होगा 18 ग्राम। ओके, 18 ग्राम वेपर, उसका वजन होगा 18 ग्राम, वॉल्यूम होगा 22 लीटर, 22.4 liter. Okay. So the point I want to bring in here is that when we talk about 18 grams of water in liquid state, this volume is only 18 milliliter. When you talk about 18 grams of water vapor, it is 22.4 liter. So 18 ml in comparison to 22.4 liter is nothing. So what we do is we typically ignore this volume, and instead of del V for the condensed phase to vapor phase transition, we simply take Vc, the volume of the vapor phase itself. All right. So this the Clapeyron equation now becomes instead of del V we write Vc. I'm sorry, the Vv, the volume of the vapor phase, that becomes del H by T del V. Okay, now you rearrange, instead of V, you write RT by P, then it becomes P del V, P del H by RT square for the partial P by T equilibrium, which again converts to an integral formula, which is dP by P is del H by RT square is dt. All right, you can simply also write DL and P is the same thing. Okay, now you can write this in a simpler form as LNP is minus del H by RT plus the constant, or within a limit of P1 to P2 corresponding to limits of T1 and T2, you write ln P2 by P1 is minus del H by R 1 by T2 minus 1 by T1. This is what is called the Clausius-Clapeyron equation, and this is an important one in the sense that you can actually find in chemical equilibrium, in chemical reactions, that the rate equation also follows this kind of an equation, right? So based on this, you can actually, knowing the del H of a reaction, you can figure out what is the effect of pressure on the temperatures. So when we do more on chemical reactions, we'll talk more on that. But this is where the Clausius-Clapeyron equation, the Clapeyron equation becomes Clausius-Clapeyron equation when, instead of a transition between condensed phases, we consider transition between a condensed phase and a vapor phase. Then we come to this kind of equation. All right. So I think what else we have? Okay, now we'll just do this and wrap it up. So how do you use these reactions that you can actually compute the latent heat, which is the enthalpy of phase transition. So for example, you don't know how much of heat is required to sort of calculate a conversion from one phase to another, and you know that you don't know this, but you can put the pressure and measure it, and you can also measure the temperature, and from this you can plot the curve between P and 1 by T, and then we find out the slope is del H by R, right? And that will allow you to compute the latent heat of phase transition. Okay. And another aspect of the condensed phase to vapor phase transition is how does a pressure cooker work? Any ideas? How does the pressure cooker work? कोई
Yes, sir.
काम वाम करता है घर में? खाना वाना पकाता है कोई? Anyway, पकाओ या ना पकाओ, if your parents do, or your mother must be doing, you might have seen her use the pressure cooker. All right, it sort of cooks things fast, or that's what it appears from outside. What does it do?
Sir,
When
the increased pressure inside the pressure cooker increases the boiling point of water, and that makes the food to be cooked faster.
Okay, increase in pressure.
Increase in pressure.
Of course, it's very normal to say that pressure cooker increases the pressure. All right, and increase in pressure cooker increases the boiling point or decreases the boiling point. What do you say?
Increases, sir.
Increases or decreases?
Raises the temperature of boiling.
Raises temperature. All right.
Yes, sir.
Anyone has got any ideas? Does it raise the boiling point or decrease the boiling point?
Sir, decrease the boiling point.
Decrease the boiling point,
Sir,
like it did the freezing point. ऐसा बोल रहे हो ना?
Yes, sir.
Okay, so let's check it whether it is decreasing the boiling point or increasing the boiling point. Okay, now here we are talking about what? We will talk about here the Clapeyron equation slight change. All right, here you know that del H for liquid too, because we are talking about water and vapor, right? Water and water vapor. So for the water and water vapor transition, what is del H? That's a huge positive. All right. अरे क्या हीट देना पड़ता है पानी को तब जाके वो स्टीम होता है. So this is an endothermic process. So del H is positive quantity here. All right. What about T? T is a positive quantity. T negative नहीं होगा Kelvin में. All right. Now what is the V of vapor? The volume of vapor. Here we are not considering del H because the volume of vapor itself is so huge that there is no point considering or deducting the volume of the molar volume of the condensed phase from here, because V here is very, very huge, very, very high, and of course it's a positive number. There's no del V here. It's only purely V. I mean, this is a positive number and this is a positive number as well. The whole thing is a positive number. All right. So for this to be in equilibrium, if we increase the pressure in the pressure cooker, then the boiling temperature of water has to increase. All right. So you might be thinking that pressure cooker decreases the boiling point and allows the steam to cook. Okay, that's the wrong thing. It's not what happens. It increases the boiling point so that water can remain at 120 degrees Celsius or some other higher temperature without being evaporated, without being vaporized. That hot water, that super hot water, actually cooks your food much faster. It's not the steam, right? So That's the correction. You might want to like change your minds, because as you know that it has to increase the boiling point of water, because that's what the Clapeyron equation says. All right. Okay, so we'll stop here. We'll take questions.
Sir, I
if there are
said that
any.
only.
All right. I'm stopping recording. We'll take some questions.